Fortunately, in the problems that we're interested in solving, we're provided with two expressions, not one. And we're further allowed to make the assumption that one of those expressions is the partial of our unknown function with respect to x, while the other expression is the partial of our unknown function with respect to y. For example, number 3 demonstrates how we can use two expressions like this to definitively recover the unknown function f. In this problem, as I just indicated, we're provided with two expressions, and we're told that we can assume that the first expression is the partial of our unknown function with respect to x, and the second expression is the partial of our unknown function with respect to y. I personally think of differentiation as moving down and anti-differentiation as moving up. So when I work these problems, I think of this type of representation. I'll start with my partial with respect to x and anti-differentiate to move up to my unknown function capital F. But as we just pointed out, there's some ambiguity in that capital F because of the nature of the constant of integration. So what I'll also do is anti-differentiate my second expression, which I'm assuming is the partial with respect to y. That'll give me two expressions for capital F, and as you'll see in a second, I can do whatever's necessary to reconcile those two expressions in order to be able to pin down what my original capital F was. Let me demonstrate with the specific expressions that we've got in this problem. I'll start by taking my first expression, which I'm told I can assume is the partial with respect to x, and anti-differentiating with respect to x to get this expression for capital F. Although I haven't written a constant of integration, I do acknowledge that there could be additional terms, and that's kind of the point of this example, is to demonstrate how I will identify those additional terms. But my next step will be to repeat the process of anti-differentiation, this time starting with the expression that I'm told is my derivative with respect to y, and performing the anti-differentiation process with respect to y. That yields this expression for capital F. Now, as I compare these two expressions for capital F, it's no coincidence that there are several terms in common between the two expressions. I have 8xy in both of them. I have minus 3x squared y in both of them. In this expression that was generated by anti-differentiating with respect to x, I have a term which is purely x. And similarly, in this expression which was generated by anti-differentiating with respect to y, I have a term which is entirely made of y terms, in this case just y cubed. Hopefully you see that the presence of these types of terms demonstrates the principle that I was just describing, that when we anti-differentiate with respect to x, I could be missing terms at the end of my expression that are made up entirely of y's. Similarly, if I anti-differentiate with respect to y, I could be missing terms in my antiderivative expression that are strictly in terms of x's. And we see examples of each of those in these two expressions. So what's my final answer? Which of these two do I use as my actual capital F? What we need to do is include all of the terms that show up through this process and then still account for the fact that there could be an actual constant of integration generated by these processes. So as my final answer, I'll have this expression here for capital F, x squared plus 8xy minus 3x squared y plus y cubed plus c. And you should take a second to verify that if you started with this original function and differentiated with respect to x, you would in fact end up with this expression that we were told at the beginning was the partial of f with respect to x. Similarly, if you start with this function, capital F, and take its derivative with respect to y, this is the expression that you end up with. So this, for example, demonstrates how we have to account for the ambiguity in the constant of integration when we're doing quote-unquote partial anti-differentiation. Continuing on to the next page of the notes, I promise that we are eventually going to use all of this to solve differential equations. But the next detail that we must address is trying to establish some criteria to determine when the previous example or a problem like the previous example will actually work out. Here's what I mean. If we start with two arbitrary expressions, are we always going to be able to imitate the process that we just did in the previous example? And the answer is definitely not. There has to be a very special relationship between the pair of expressions in order for them to work out the way that they did in that last example. Let me demonstrate by showing you a case where things don't work out that way. Here are two expressions that I've referred to as capital M and capital N, and I claim it would be impossible to use these the way we use the two given expressions in the previous example to recover an original function, capital F. Let me demonstrate those steps quickly. Here I've tried to use the given expressions capital M and capital N the same way I used the given expressions in the previous example. That is, I was told to assume that this capital M is the partial of our unknown function f with respect to x, and this expression capital N is the partial of our unknown function with respect to y. I anti-differentiated appropriately, so over here on the left I have anti-differentiated with respect to x, and on the right I have anti-differentiated with respect to y. So, as with the previous example, I have two separate expressions for capital F. But in this case, it's impossible to rectify or reconcile those two expressions. When we look back at the previous example, the two expressions for f that we generated only differed in terms that were built exclusively out of one variable. And that variable was the variable that we had just anti-differentiated with respect to, as I explained. So notice in the previous example, the terms that differ in our two expressions for capital F are terms that are exclusively built out of x's and y's, respectively. In the current example, that's not true. The terms that differ are built out of x's and y's. Here I have an x squared sine of y. Here I have an e to the negative x y. And it is impossible to somehow combine these two capital F expressions into a single capital F such that these would be appropriate partial derivatives. And maybe you think I just made the wrong choice for M and N as it regards associating them with the partial derivatives, but it doesn't matter. If I was to switch so that M was considered f sub y instead and N was considered f sub x instead, I would still run into the same problem. So this leads us to the question, is there some sort of criteria so that if I'm presented with two expressions, the way we were just presented with this capital M and this capital N, if we're presented with a pair of expressions, is there some way to test whether we will be able to use our process from the previous example in order to recover or reconstruct an original antiderivative function, capital F? And the answer to that question, fortunately, is yes. The criteria hinges on a property that we identified in a much earlier example, and it boils down to the requirement that for our antiderivative function, capital F, the mixed partial derivatives must be equal. So as it says here, if I'm presented with two expressions, M and N, and I believe that those are candidates for the partials of capital F with respect to x and with respect to y, I'll even write that. I'll even write capital M is equal to f sub x and capital N is equal to f sub y, as I did just a second ago. Then I need these mixed partials to be true. So in order for this pair of expressions to really function as a pair of partial derivatives, I can check this pair, this identity or this equality between the mixed partials. And just so we're clear on this notation, when I'm presented with a pair of expressions, I will assume that one is the partial with respect to x. Typically we call that M, and we'll assume the other is the partial with respect to y, which we'll typically call N. But the derivatives that I'm targeting are the partial of f with respect to x and then y. So this expression, which I'm assuming to be the partial with respect to x, I need to take its derivative with respect to y in order to generate this mixed partial expression. The opposite, more or less, is true for this second expression. Here I've expanded the derivative notation as we did earlier to demonstrate notationally what I just said. We're going to take the expression M which we're assuming to be the partial with respect to x, and we're going to apply the derivative with respect to y to that. So if I apply the derivative with respect to y to m, clearly I would write that m sub y, and that would yield an expression which I'm assuming is f sub xy. I enact the corresponding process on the other expression, and to reiterate, I want these two mixed partials to be equal. Therefore, I want these two partial derivatives, which are written in terms of the expressions m and n, I want these two partial derivatives to be equal. If these two partial derivative expressions are equal, then we have satisfied the criteria, which indicates that the original expressions m and n will function as an appropriate pair that I can build an antiderivative capital F out of. Let's demonstrate that criteria in, for example, number 4. In each of the parts of this example, we're provided with two expressions, a capital M and a capital N, and we're asked to test if they could serve as the partial derivative pair so that we could reconstruct an antiderivative function capital F. That is, we're being asked to test if these two partial derivative expressions are equal. So I'll take my expression m and I will differentiate it with respect to y as required. And I'll take my expression n and differentiate with respect to x as this criteria requires. And those two expressions are in fact equal. That indicates that the two original expressions, capital M and capital N, could be used as first order partials. We would call them f sub x and f sub y respectively. And then we could use those to reconstruct an antiderivative function f as we did a few examples ago. Let's try that again in part B. Calculating the appropriate derivatives in this case indicates that these two expressions are not equal. Therefore, this m and n pair can't be used to reconstruct a capital F. Let's try it one more time in part C. In part C, the appropriate partial derivative expressions are equal. So we could use this pair to reconstruct a capital F. After all of that build-up and background, we're finally ready to discuss exact differential equations. We've done a lot of background work building the foundation so far this lecture. And the good news is, if you understand everything we've done so far, we've basically done all of the work. What we need to do now is simply state the definition of an exact equation and talk about how the structure that we've been discussing generates the solution of such a differential equation. Put simply, the general solution of an exact equation has the form capital F equals C. That is to say, if we can identify that our differential equation is an exact equation, then the answer that we're after, the general solution, is capital F equals C, where capital F is one of the original or antiderivative functions that we've been talking about through most of the lecture. So that's the solution of the differential equation. What does the original differential equation look like? We actually generate the form of the differential equation by looking at this simple equation, F equals C, applying the chain rule from calculus and doing some rearranging so that the structure of an exact differential equation is provided by this equation here. So an exact differential equation will have the form some expression times dx plus some other expression times dy equal to 0. The dx and the dy are generated by taking our first derivative and separating that derivative the way we did in the previous section when solving separable differential equations. And these coefficient expressions, as we indicate here with this notation, we want to assume are the derivative with respect to x and the derivative with respect to y of our unknown solution function. So how can we test? What criteria do we use to determine if given expressions can function in that way? That's exactly the criteria that we just discussed and demonstrated in the previous example, and this is explained in our definition. Definition 1 indicates that a differential equation is called exact if it meets two criteria. First of all, it must have a specific form. The form that it must have, as we just pointed out, is some expression times dx plus some expression times dy equal to 0, where the dx and the dy are generated by separating the first derivative term dy dx. So that first requirement is pretty easy to check because we just have to see if the equation can be algebraically manipulated to have that structure. But as we pointed out above, I can't just pick any pair of m and n and be able to reconstruct a capital F out of them. There is the additional requirement that this partial derivative expression m sub y equals n sub x must be true. So if our differential equation has this general structure and this relationship holds between the two component expressions m and n, then we do have an exact differential equation. And to find the solution of that exact differential equation, we assume that the m expression is the partial of f with respect to x. We assume the n expression is the partial of f with respect to y, and then we just use the appropriate antidifferentiation processes to reconstruct the antiderivative function capital F. Once we've found f, our general solution will simply be that antiderivative function capital F set equal to an unknown constant c. So we're finally ready to try to solve some differential equations. Let's take a look at example 1. In example 1, we first want to test that the expression is an exact equation, and if it is, we'll find the general solution. The equation provided in example 1 already has the general structure that's required, so we can name these coefficient expressions capital M and capital N respectively, and then we can calculate the necessary partial derivative expressions and check if they are equal. In this case, the two expressions m sub y and n sub x both equal 3, so m sub y does equal n sub x. This confirms that our differential equation is an exact equation. So to move forward to find the general solution, we'll imitate the process we used a few examples back. I'll start by making the assumption that my m expression is the partial derivative of my unknown f expression with respect to x, and then make the appropriate similar assumption about my expression n. Then I antidifferentiate each of those expressions with respect to the appropriate variable to generate two separate expressions for my capital F. As we saw in the previous example, the terms in these capital F expressions that are mixed, the terms that contain both x and y terms in them, agree between these two expressions. The terms that disagree in these expressions are the terms that are exclusively made up of x's or exclusively made up of y's as appropriate. So I can reconcile or sort of merge these two expressions for capital F to come up with a single final expression for capital F. And then if I take this expression for f and set it equal to an unknown constant, that equation serves as the general solution of my differential equation. So we're done. Notice that this expression is typically going to be pretty complicated, and it's not the type of expression that I would want to or potentially even be capable of solving for y. That implies that my solution will be an implicit expression for my general solution as opposed to an explicit expression, but that's okay. I will still use this as my general solution to the differential equation. If I was provided with initial condition, I would incorporate those now in order to solve for the unknown constant c, but in this particular problem, initial conditions are not provided, so that's my final answer. Let's take a look at another example. I'll follow a similar process in part B, but I notice right away in part B that my differential equation currently doesn't have the proper form. Recall that I must do whatever manipulation is necessary so that my differential equation is some expression times dx plus some expression times dy equal to 0. So I have a few steps of algebra to perform before I can test my partial derivative criteria. Here I've simply brought the negative 2xy from the right over to the left so that I have 0 on the right hand side. Next I will separate my derivative. And here I now have an equation with the required general structure, some expression times dx plus some expression times dy equal to 0. I name those coefficient expressions m and n as appropriate, and then I can calculate the partial derivatives that are required to test if this is an exact equation. And sure enough, the necessary first-order partial derivatives are equal, so the criteria is satisfied, and this is an exact equation. Next, I'm ready to use the m and n expressions, making the appropriate assumptions about their structure and their relationship with respect to f in order to reconstruct the capital F antiderivative function. Applying the appropriate antidifferentiation techniques, I end up with two expressions for capital F as expected. So my final step will be to merge those two expressions into a single expression for capital F, then set that capital F equal to an unknown constant, and that'll be my general solution. Let's take a look at another example. Part C. Let me complete the work for Part C, and then I'll discuss a few of the key steps. I first have several steps of algebra to complete just to manipulate my equation into the proper structure. Identifying the necessary component expressions m and n, and then calculating the required partial derivative expressions indicates that these two partial derivative expressions are not equal. So this differential equation is not an exact differential equation. So I cannot proceed to find the general solution as we have in the previous examples. It is possible that this differential equation could be linear or separable, and we could use one of the techniques that we've discussed in the previous two sections. But for the purposes of this example, I'm just going to indicate that it's not exact. Therefore, we cannot use the procedure that we have identified in order to be able to find its solution. So we won't be able to find a solution to this differential equation. Let's move on to the last example. Here I've performed a few necessary steps to get my differential equation into the correct form, and I've calculated the necessary partial derivatives, and in this case the two quantities m, y, and n, x are equal. So this is an exact equation, so I can proceed with the solution technique that we've used in the previous example. And following the necessary steps, I get a general solution of xy equals c. This is a case where my solution is simple enough that I could explicitly solve for y, but I'll leave my solution as it's written. And I want to make one last final note. We have solved the differential equation given to us in Part D using the techniques of exact differential equations that we've discussed in this section. But if you look at the structure of this differential equation, you might recognize that it is both linear and separable. So this single differential equation given to us in Part D could be solved using any of the three techniques we've discussed so far in Chapter 2. This is relatively rare, so you shouldn't expect to be able to apply different techniques to a single differential equation, but I just wanted to point out that in this particular case, that is true.